Welcome to the Lecture 4 Q&A. There was a lot of confusion today because I left out one of the videos in the playlist for Lecture 4, the one about lambda expressions. Right after the Q&A, at about 9 a.m. Pacific time, I added that video in. So hopefully you saw it. If not, you might have seen this keyword lambda before it was ever explained, and that could cause a great deal of confusion. If that happened to you, hopefully the questions and answers in this Q&A will help clarify. And I'm sorry if that happened to you. If not, you'll notice there's a lot of questions about lambda, which is fine. Even if you saw the video, you probably have questions, and this video might contain some answers. I've edited out the students, so you'll just see Hani and I answering questions. And occasionally I'll jump in like this to repeat the student's question if I think that will help you understand the answer. Yeah, so the question is, what is a lambda function and a lambda expression? Because they were used in one of the lecture videos, but they were not explained. And for that, I apologize. So a lambda expression is kind of like a def statement in that it creates a new function, except that it has a different syntax. And what's special about the syntax is that it doesn't give the function a name. So normally you'd write def f of x, return x plus 2. And you would create a function called f, which adds 2 to things. A lambda expression doesn't include this f. Instead, it does include the formal parameter name, x, so that you know how to refer to something. It doesn't include the word return, but it does include the return expression. And evaluating this creates a function. But this function doesn't have a name. So we call it a lambda function just because there's no other good way to refer to it. Now, the other interesting thing about a lambda expression, other than it has a slightly different syntax than a def statement, is that it is an expression, meaning you can put it into some larger expression. So I could, for example, say g equals this lambda expression. I don't actually need the parentheses. And now I do have a name for this thing, g. It's still a lambda function, but I can refer to it as g, and therefore I can add 2 to things. That's a 9, not a g, using the function that I created with the lambda expression. And yeah, okay, so I'll stop there. Hani can explain why this
Two things, John.
exists.
Can you make me a co-host so I can manage the
Yeah.
participants, please? And Tyler, the way to think about, I mean, John said it exactly right. It's an anonymous function. It's a function like any other function. It just doesn't have a name. And it may not be obvious why you want to do that, but you'll see downstream sometimes it's nice not to pollute your workspace with a lot of function names when you don't actually need them. Yeah. So think of it as just as an anonymous function, and with a slightly different syntax to how you define a function.
And I think the question is, what are these? How are they being used together in the demo? And can we kind of trace through how that works? And that is exactly what we will do. So in this example, search was powerful, but rather simple function. It takes in another function, f, and returns the smallest non-negative integer x for which f of x is a true value. So it basically just searches through all the integers until it finds an x, where when you pass it into f, you get something true. So if we wanted to know oh, this is probably the demo where the lambda showed up.
I think that's where you use this 3.
It must have been very complicated. Okay, so let's use square to do something particular. Let's say is 4 squared is a function. Now, how would we use square to do this? Well, we would return whether square of x, square of 4 equals x. So in this world, I'm pretending I don't really know how to square things. I don't know what square of 4 is. I mean, I do. It's 16, but let's pretend we didn't and we wanted Python to do the work. Well, now we have a function that is only true for 4 squared. So if I pass in 3, it will say no, 4, no, 5, no. But if I keep doing this for a long time, it will say, oh, 16 is 4 squared. Now, instead of me typing this out, I could use search to do it for me. Search for the smallest integer that is 4 squared. And it will tell me it's 16. So by using square and search together, I've created a procedure for searching the integers until we discover 4 squared. That was part of the demo. So why don't I pause there and see if there are questions. Otherwise, I'll go on to what this has to do with inverse.
Let me add one thing too here. Notice that what is happening here is that the function is 4 squared is being passed into the function search. We're not calling, there's no parentheses around that call right there. So it's being passed as a parameter and then used, of course, to evaluate in the conditional inside of that while loop.
Okay, so sounds like maybe this made some sense. What if we wanted to go the other way and find a square root? Well, then we could write a function is square root of 16. And what would this look like? This would return square x equals 16. Okay, so now we have a function where I don't know how to take square roots. And like I actually don't, it's some procedure that would compute the square root, but this is the kind of thing that I kind of just memorize. Is square root of 16 is not true for 2 or 3, but it is true for 4, but not true for 5. So if I run a search for what is the square root of 16, it will tell me that it's 4. So in this sense, we've inverted the square function. Square goes from 4 to 16. Now we have a procedure for going from 16 to 4, which I did in a specific case here by writing an is square root of 16 function. But this general format, I think I could write in terms of not just 16, but in terms of anything. I wish I knew exactly how my demo went, but I think it was something like, we're going to invent the square root function, which takes in some y, defines a new is square root of y, x, which is just like this, except for instead of hard coding 16, we write y. And then we can return a search for a number that is the square root of y. And now we can take the square root of 16, and it ran forever because I did something wrong. I never returned.
Yeah.
Rookie mistake. Sorry about that. And return the square root of 16 or the square root of 25. Now this will only work for perfect squares. But we've built a square root function that's kind of a generic version of the specific procedure that we did for 16, which is to create a function that tells us when we found the square root and then search using that function until we find the square root. Terrible way to find square roots. It's like very inefficient, but the fact that we were able to do it is kind of interesting. So that was the core of the demo. And then what about inverse? Well, let me pause here and see if there are follow-up questions, and then we can talk about inverse. Yeah, that's right. So the question is, what does positive have to do with any of this? And the answer is nothing.
Nothing. It was just
Um,
another example of using the search function. Yeah.
Okay.
By the way, let me just point out a couple of things in this example in the Python interpreters. Notice that there's one function, square root. That's what's in the global frame. Inside of that function is another function definition. The scope of that function is square root of y, is only visible within the square root function. Yeah, I think we'll talk more about that on Friday in the environments. But that is a function definition within a function definition. And the reason we do that is because that's the only function that needs to do it. And so it's scoped within that function. Yeah. So watch those indentations. That what's indented will tell you about the scope of things.
So it's probably worth really quickly just following up on the what's a lambda function question
Yeah.
by finishing this definition of an inverse, which I wrote in this particularly tricky way. But let's not write it that way. Let's take the code that we built so far and make it even more general. So the code that we wrote so far said make a square root function and then define the square root of y and then search for it. But this is specific to squaring, right? And
Sorry, John,
instead,
you forgot the return again right there.
oh, I did it again right there. This is specific to squaring, which is not what we wanted. We wanted to not just take square roots, but to take any inverse of any f. And we wanted to do this by calling f of x equals y. So now we've sort of just generalized from squaring to any f that might come along. And then we've created an inverse of f function, which if we pass square as f, we'll get the square root. See if this actually works.
While John is doing that, I'll say I prefer this construction to the lambda construction. You can see the lambda construction is particularly concise. One line of code, really elegant. I find that code hard to parse. So those two things, what's commented out with the lambda construction and what's sort of a little bit more clumsy is our equivalent. I'll say sometimes clumsy code is not bad because it's easier to read. There's this balance between, oh, this is a nice, elegant one line of code, but it's a little obfuscated. And we sort of course, have to find that balance.
Yeah, in particular, this leaves out all the names. And the names are pretty helpful. Like, yeah. What does this do? It returns the inverse of f. So if you name things well, it's sort of easier to see what's going on. Now, this is a function that returns a function that returns f of x equals y. That's kind of or it returns the result of searching for f of x equals y. And this says the same thing, a function that takes y, which searches for the result of a function that takes x and computes f of x equals y. So in that sense, they do the same thing, but this sort of makes explicit what the different pieces are. Good question. Okay, so the next question is, here's an example from the textbook. What on earth is going on? Compose is a higher order function that basically takes two functions and says, when an actual value, a number, let's say, comes in, first apply g to it. So if g is add 1, then we're first going to add 1. And then apply f to that result. So if f is, I don't know, square, then we'll add 1 to x and then square that result. So if x were 3, then we would add 1 to get 4, and then we would square it to get 16. But compose 1 doesn't say what f and g are. It just says that there are some functions. It has yet to be determined what they will actually do. All compose 1 says is, once I know what f and g and x all are, here's the work that I'm going to do. I'm going to apply g to x, and then I'm going to apply f to the result.
And so to be clear, Mishan, this is like a standard mathematical operation. This is not a Python issue. Function composition is a normal thing. You apply one function, you apply another function to that. And this Python function is simply taking two functions as input and do function composition. Yeah. And now for the ugly part with the lambda expressions.
Now, this part says it's time to fill in f and g, but not x. So f is going to get filled in with, and then you have to know how to read lambda expressions. So the way you read a lambda expression is a function that takes x and returns x squared. That's going to be f. And this says a function that takes y and returns y plus 1. Okay, so that's going to be g. So here, I picked a lousy name, f. This could have been something else like h.
Yeah.
I mean, no reason to make the example even worse than it already is. Okay.
By the way, let me interrupt just for a second, Mashan, here and say, we could have written this another way without lambda expressions. So I could have passed in the function square, which takes a single input and returns the square. And I could have passed it a function name called add1, which takes a parameter and adds 1, and that would have been exactly the same. It's just a little convoluted here because of lambda expressions. Yeah? Good.
Okay, so now h is something that takes in an x, adds 1 to it, and then squares it, which means that h of 12 should be 13 squared is 169. Now, the environment diagram shows you how that happens. And how that happens might actually be more complicated than just thinking about what this code does. So abstraction is valuable in this case, I think, in that if you think of like, oh, this adds 1 to things, this squares things, and compose says first add 1 and then square, then you can predict what this is going to do without drawing the environment diagram. But you also could draw the environment diagram to watch the step-by-step mechanics. And what that looks like is that calling compose creates a local frame with an f and a g, which are assigned to these two different lambda functions. And since they don't have names, it's hard to tell which one's which. But if you look at the code, you can see, well, this is the one that squares, and this is the one that adds 1. It returns a new function. So neither f or g has been called. All of the calling happens when you call h. So h is the name for the return value of compose1. And when you call h, you get a lambda frame. Why is it a lambda frame? Well, because you just called a lambda function. Why does it have x here? Well, because you called this lambda function, which has x as its formal parameter. You've bound this x to 12, and then you execute the body of this function, which means you have to call f of g of x. There's no f and there's no g here, but they are here. And these are accessible. This is what we'll talk about on Friday in some detail, is that when you've defined this function inside of compose, then it can refer to this f and this g. When we talked about this in lecture today, but we never really drew the environment diagrams. That's the job for Friday. But the mechanics of it in an environment diagram is that when you look for a name, you're looking for f, you first look here in the current frame. And if you don't find it, then you look in the parent. And the reason this has a parent of f1 is that it was created in the f1 frame. And you can see it has a parent of f1. That's where this parent came from. And so you find the f and the g there. They're both lambda functions. And that means you can call f, which is a lambda function that adds 1 to things. You make another call for something that squares things. And then you finally get 169.
So when you see the lambda, John said it just right. Read it like this: lambda. This is a function. Next thing, that takes a parameter. After the colon, returns this thing. So notice that it just doesn't have a def. It doesn't have a return statement. So you just have to sort of read it slightly differently. But it's exactly a function definition without a name. John's going to do the example that I suggested.
Yeah. So we cleaned that up. Well, I'll leave the old one there so you can see the contrast. But the nice version would be compose 1 of square and add 1. This would do the same thing. We just wrote the functions using def statements. Right. And in fact, this could be written using def statements too. We could have said, I want to def the composed function, which takes x and returns f of g of x. And that's what I want to return, instead of trying to cram it all in one line. And now I have equivalent code. If I ran all this, then you'd see the same environment diagram, except for functions have names along the way, like composed and square, instead of everything being a lambda. So it's easier to follow.
So you can see why the lambdas are nice. You can see how much less code you had to write. We didn't have to define square. We didn't have to define add 1. We didn't have to define a function within a function. So it really tightens up the code, but also makes it a little cryptic. In the real world, John, do people really use lambda functions? Or what's the protocol in the industry?
I think it's somewhat unusual that you'd see it here.
Mm-hmm.
It's quite common that you'd see it here. So if your goal is to pass in a function that's just does something really simple, that's where you tend to see lambda expressions.
Yeah.
Because it's nice to just kind of say like, oh, I want to call this function, whatever it is, on this thing, and it happens to be a function, so you use a lambda. So they do appear out there in the world. And yeah, I guess I've seen them a lot more recently in like machine learning frameworks. People use them, but other than that, they were not terribly popular in Python. They're really popular in other programming languages, like Ruby uses them a lot, and JavaScript uses them a lot. So it really just depends on what programming language you're using. Okay, so the question is, for this example from lecture, where we had a function that returns a function, and then we called it twice with this very bizarre syntax where we had 2 parentheses in a row. What does this mean and how does it work? Well, a normal call expression looks like f x, right? And that's actually what this looks like too, except for we don't have the function named already. We need to write an expression to build the function that we're going to call on 2, and then we call it on 2. So kind of the right way to think about this is that we're doing a bunch of work in order to figure out what function to call, and then we're going to call it on 2. It turns out that figuring out what we're going to call it on is really simple. It's just 2. But we have a compound expression in order to figure out what function to call. So I'll leave those parentheses in there. They're not going to do any harm. When you evaluate this whole call expression, first you have to figure out what function you're going to call. And in this case, we don't just look it up by name. We do some work. We call makeAdder on 1, which creates a new adder function and returns it. Now, where is this return value going? This adder function is being returned as the function of this call expression. So this return value is basically telling me, here's the function you're going to call on 2. Then we can call that on 2. So here we see a frame for adder, which is this adder function that just got returned, is now being called. That's why it gets its frame. And with its formal parameter y bound to 2, that 2 came from here. So when you have a compound operator expression, that's the thing before the parentheses in a call expression, you have to evaluate it first before you can call whatever function. And this better evaluate to a function, otherwise it will crash. If instead this evaluated to 12, it would say you can't call 12. But it evaluated to the adder function, and so we were able to call that. And what does that do? That adds 1 to 2, and we're done.
So the other way to see this is if we had written f is equal to makeAdder of 1, and then on the next line, call f of 2, that's exactly the same thing. We've just done it in 2 steps to make it explicit that f is the function returned by makeAdder, and then we apply f to 2. So that's just a shorthand for those 2 lines of code.
Next, a student wanted to clarify that makeAdder is returning a function and not a value, such as a number.
That's right. And you can see that because if you look at makeAdder, what's the body of the function? It's a function definition, but that's not the important part. The important part is the return adder. It returns the name of a function that gets shoved in this example, to f. F is now just a synonym for a function, adder, and then you can apply that downstream.
And a common mistake, not that you would make this mistake, but a common mistake is that people will try to call this because it looks unnatural just to name adder. So you want to call it, I don't know, on maybe x or something like that. But what this will do is it will compute a number, and you can't call a number down here. So this would eventually give us an error, and it would sort of do the wrong thing. So this would add 1 and 1 together to give us 2, return 2, and then you can't call 2 on 2 because this integer is not callable, and you'd run into a problem. So this adder is bare, just a name, not a call expression for a reason.
Oh, what I see. What can you put into a lambda expression, I think is the question. Can it only be an operand in a return statement? Is that right? Right. You can put whatever you want in. Oh, actually.
In Python, it is quite restricted.
No, that's right. In Python, yeah, I think it's only a return. You can't put like a loop or a conditional or anything, right?
That's right. It has to be just the return expression.
Yeah.
Pardon me for a moment.
Yeah. So it can only be a return statement. And that's because you notice there's no explicit return. Yeah. So it's whatever shows up there. So it's a pretty limited expression what you can put in there. Now, I think you can.
Yeah, this doesn't work.
Right. Exactly.
You can only write x plus 1. You can't even write return. That's not allowed. You just have to
right.
write what it's going to return. So this only is allowed. You're only allowed to use this for stuff that's very simple. Now, you could say like, oh, I want to do f of x, and f could be arbitrarily complicated. Like this could have a while statement in it. So there's no limit to the kind of power of what a lambda function could do. But in terms of its own code, it has to be very simple.
I'm going to let John put it back up. So I think where you're asking, if I just said make adder of 1 and nothing else, it would have called make adder with 1. It would have returned the function, and that's all that would have happened. So it would return something, but just the function. It just simply wouldn't have evaluated it. Well, it depends what you want to do. If I want to assign make adder of 1 to another function, that's fine. I can do that. I don't have to evaluate it. But if I want to actually go ahead and do the evaluation, then yes, I need that other parameter, which is, of course, the y parameter. So this is, you're asked, the question is the difference between that sort of compact version of if and then the full-blown. I don't know if there's an easy answer to which one is more or less common. I think part of that is stylistic. I, for example, like the if, elif, else clauses. I find them easier to read. But I think John may have a different opinion. This may be a style issue. Is I think for really simple things, you tend to use the simple predicate, like just short, bite-sized things. But I wouldn't do it like if I had 4 lines in the conditional and 3 lines in the else, I wouldn't write it like this. I find it confusing. So things that are very compact, I think you use this notation, and things that are a little more complicated, then I think you probably write out. John may have a different opinion about that, though.
No, Hani's exactly right. Writing this in like a real program is exceedingly rare. But I showed it to you, and I told you like you don't need to know this, but I'll show it to you because you will see it in someone else's program one day. Writing programs is very collaborative, and you end up reading other people's code. So I figured I'd just let you know that it exists. But yeah, but there are cases where it shows up. Oftentimes it's like in the body of a lambda where you're not allowed to write an if statement, but you're allowed to write this. And so, people do use it every once in a while, like it's in the language for a reason, but exceedingly rare. So it's almost always the case that people will use a normal if statement instead.
Yeah. I think John's exactly right. You should know that because when you see it, you should know what it is. It's also, I remember back in the day when we used to code in C, a similar construct was very popular also. You would see it a lot in code and make the code very compact.
The next question was, is lambda just a convenience, or are there instances where you have to use lambda, or it's more appropriate to use lambda instead of a def statement?
Yeah, that's a good question. I'm going to give my answer. We'll see if John has one. One of the reasons I like the lambda is it cleans up the namespace. When you define a lot of functions, your namespace tends to get a little crowded. So I like anonymous functions sometimes just to keep that clean. But maybe John has a better answer.
Yeah, so lambda expressions don't give you any more power than you already had. It's not like you can now write a program that you couldn't write before. And so you don't really need them at all. You need to know what they are, again, so that if you see someone else use it, you can figure out what their code is doing. But it really is just a way to make things more compact. Most functions should have names because the name tells you what they do. When it's really obvious what a function does, maybe it doesn't need a name, and then lambda expression is a reasonable candidate. For the next question, a student sent us an environment diagram for the section in the textbook about Newton's method, which is fine for you to read. It is not required reading. It is no longer part of the course that you need to understand this example, but it's still a good example. And so we talked about it for a minute, but didn't really answer the question. Right. Thanks for this question. There's a section in the textbook about an application of higher order functions called Newton's method. And it's, I think, quite a nice example. I didn't come up with it. It's borrowed from the textbook that this course was based on. But we've taken it out of the course because it requires you to know something about calculus, and also it's just quite involved. So I left it in the textbook because I think it's worth working through if you really want to, but you do not need to understand it. It's intentionally been removed from the course, although it used to be part of the lecture series, so that you can kind of focus on more reasonable examples. Now, the example really kind of takes a full lecture to explain, so I guess I won't attempt to explain the entire thing now. I'll give you a little gist, which is that there's a very generic kind of iteration about searching for the right answer for something, kind of like what we did earlier in this Q&A when we were searching for the square root, except for this can do it more cleverly because you can pick any way to update you want. So in our search, we started with 1, 2, 3, 4, 5, 6, but maybe there's a better way of searching for a numeric value than just counting up the integers. And that's exactly what Newton's method, which is like an application of differential of calculus, lets you do. And yeah, so it's kind of like a smarter version of searching for numerical answers that lets you not just compute square roots of the integers, or sorry, of perfect squares, but it could let you compute the numerical approximation to the square root of 2 or something like that. How would you learn more about this? Well, there is a whole video series. I thought it was in the textbook. If it's not, maybe I'll link it there.
I don't think it is, John, because it might be worth, we can add a link to that.
Okay.
If you search online for Newton's method, this is a standard numerical method for finding zeros of a function. It's a really lovely algorithm. You have to know a little bit of calculus. You have to remember what a derivative is and a tangent and things like that. And so if you're interested in going off on that tangent, oh, wow, that was funny. You can do that. But I think John's right there. This would take too long for us to walk through this whole example here, okay?
The next question was about how multiple assignment works when you have 2 names on the left side of equals and 2 expressions on the right side separated by commas, and in particular, how that worked for the Fibonacci example from lecture.
So the most important thing to remember when you have this kind of command is the right-hand side is fully evaluated before you do the assignments, right? So it's not like you go left to right, do the left one, assign it to the left variable, and then do the right one, assign it. So the whole right-hand side of the assignment operator gets evaluated. You get values there, and then you assign them to what's on the left-hand side. And in that regard, there's no crosstalk, right? So yeah, John did a nice visualization here so we can see it.
Yeah, the stuff on the right is evaluated until you're left not with names, but with numbers. Right. So if we're about to do this one, we look up cur is 3, we look up pred plus cur is 5. Now we have 3 and 5, the numbers, and we then assign the new names pred and cur to 3 and 5. And therefore, it doesn't kind of get mixed up.
Right. And by the way, same thing, if I just said x is equal to 3 plus 7, I fully evaluate what's on the right-hand side. I break down that expression until I have a number or a string or a Boolean or whatever it is. And then I go and do the assignment.
Yeah, great question. So if you create a lambda function by evaluating a lambda expression, do you have to do something with the result immediately or risk losing track of it forever because it has no name? And the answer is yes. If I just write this on a line, and then on the next line, I want to call it somehow, I can't call it with f because it doesn't have the name f. It's effectively lost. Just like if I had written 12 here and I had not done anything with it, that 12 would be lost unless I did something with it. Now, what can you do with it? You can assign it a name, then you could refer to it later. You could pass it in, and then f could refer to it. And then, like, if you're in the context of another function, you could return it, and then whoever called f could refer to it as the return value. But if you just leave it there alone, or I guess you could call it, that's another thing you could do. But if you just leave it alone, then there's no way to access it later. It's effectively gone.
Great. So to summarize all that, lambdas are just anonymous functions. They're just a shorthand way of writing a def statement. They're convenient when you're passing things as parameters or defining things within functions. That's it. And again, I want to just emphasize, particularly in the early days of looking at the lambdas, read them in a very specific way. You see lambda, this is a function. It has a parameter x, and it returns whatever is to the right-hand side of the colon. And remember, again, in Python, all you can do is a return. So these tend to be very simple and compact. Thank you. That's it right there.
Sorry, I'm probably being distracting.
And so it's conceptually, it's not really new. It's just a different way of writing it.
Good question. So the question is, when you're defining a lambda, could you put a function here? And the answer is yes.
Yeah, if f is defined.
If it's defined before.
If f was already something, then I could have a function that takes in x, ignores it, and just returns f instead. And I guess we'll call that g. Now this is kind of a funky thing. This says take into, ignore it, and return f. So now g of 2 is going to give us a function that adds 1 to things. And if we want to add 1 to 7 and get 8, then we could do that.
You can also return a lambda, right? So the lambda function can return its own anonymous function, right? It can just be another lambda expression. I think we've already seen an example of that, in fact.
That's true. So like what that would look like is if we didn't have f at all, and instead we had return a function that adds 1 to things. Then here, this doesn't refer to x, so 2 is still ignored, and it's just going to compute 8 again.
Okay, I might be admitting people into your 9 o'clock meeting, John. I'm not really sure. But I think that's it for time. Thanks, everybody, for the great questions. We'll edit this video, and it'll be online, in a day or so.
Yes, and so sorry about not explaining lambda before using them. All right, have a good day,
everybody.
folks.